Yeah, thank you, IPAM, for organizing this special session for tensor decomposition, tensor network. So, like we talked about the tensor chain decomposition, love tensor network. We will also show you how to decompose this kind of tensors, this special tensor, efficiently, especially how to deal with instability of this tensor network. So we go a little bit far from the ordinary tensor decomposition, like for example, the canonical periodic tensor decomposition, the Tucker decomposition, the block term decomposition. But we saw the link between the ordinary tensor network, the ordinary tensor decomposition, and this kind of tensor network. We also discussed about the sensitivity, and we see some similarity between the first two talks by in this session, and we shall do some algorithm we can help you to decompose to find the tensor chain decomposition, the best tensor chain decomposition in my opinion. We also show you several new application of the tensor chains. So let's first start with the stress tensor network. We call it the MPS, the metric product space, or some people also call it tensor train. This introduced by Ivan Vasilides around maybe in 2009. So the idea of tensor train is that it connects it model an order n tensor, high order tensor by n core tensors. It can be metric or it can be order trees. That the core tensor here interconnected, and we have here a stress tensor network. So you can see here how they can data y, tensor y can be represented by a tensor train model. So they have some outer product of the fiber, the tensor, the first core tensor, the second core tensor to the last core tensor. And we can write here some shorthand notation. And this notation is show you that the train contraction between two core tensors, Z1 and Z2, G2 and G3, something. And we have R1 to Rn, and minus 1, it represents the range of the model. So we have many applications. The tensor train, it have many applications in, for example, very recently, it can be applied to deep learning, compress some model in convolutional neural network, but it has some problem. It has some problems. So if you try with tensor train for real data, you want to get some good approximation. The problem is that the intermediate range is really high. So what is intermediate range? So you have here several core tensor. And the first core tensor you have R1. The second core you have here the size of the dimension of the core, second core tensor, the R1, I2, and R2. So the intermediate core tensor can be inside in between inside the network. So it can be G3, G4 sometimes. So the size of the core tensor G2 or D3, G4 is really high. And in this case, this if you compress, you want to have a good compression. In this case, you lose the kind of property due to the high intermediate range. So how to deal with this problem? A very clever idea introduced in 2009 by Kromsky. So what if we wire the first and the last core tensor together? So in this case, we don't have any intermediate core tensor. We don't have the first, we don't have the last core tensor, and on we have here interleave. And in this case, the range will be equally or maybe uniformly distributed. And some example, some simulation is so that this confirm the observation. So very clever idea. But then did know any model is perfect. What is the problem with this model? So okay, let's first go to the definition of the model. So we can draw something similar to the tensor train model. You can see here that the outer product of the fiber taken from the first core tensor, and then you have the fiber from the second core tensor, the last core tensor. We also write here at the element y expression for the y tensor here. So in this case, you have the trade. You click the slide one, the slide of the the first core tensor, multiply with the vertical slide in the second core tensor, and to the last, the slide of the last core tensor. So again, let's introduce why. Okay, I'm seeing that I missed something point here. Okay, let's continue. So we have in 2011, Espich and his colleagues, they proposed some algorithm for ALS for Tensor Train. And the first algorithm is very simple. So this is the ALS. So it's very similar when you apply, when you decompose like CBD decomposition, Tucker decomposition, block term decomposition. The idea is that you flatten the tensor into a matrix and you formulate the optimization problem. You can see here this form, and then if you fit on the core tensor, but it set the first core tensors, and in this case you have something like this form. You can find the closed form expression for the 8. And in this one, we show that this is the mode 2 unfolding of the first core tensor. Okay, we train because here we have only all the 3. So we put, instead of G1, G2, G3, you have 3 core tensor A, B, and C. So if we fit B and C, we can see that we can find closed form expression of that for the 8 easily. And it's right here, the update rule. So there are many other algorithms for Tensor Train. And also, for example, the DMRG algorithm for Tensor Train, we also have similar algorithm. But again, I already mentioned to you that no model is perfect. The problem with Tensor Train is that because the love is a beautiful idea to handle the high intermediate range in Tensor Train, but then it raises another problem, a severe numerical problem, as it mentioned in the paper of Espich and Hertug and BD tested for Hertug, and also in the book of Landsberg 2012. And the problem is basically very severe when the we have, when we're unfolding the core tensor into a matrix, and the second dimension, it is the first dimension, this will be IN here. So in this case, we have the problem, the tensor decomposition become more unstable. So let's first go show you the first example. So the tensor are very small. Let's see here, the tensor only of the size 4 by 4 by 4. It composed from 3 core tensor of the size 4 2 by 2. It means that the core tensor had the range, the data had the range 2 2 2. We just randomly generate the core tensor. We compose, and we have like 1,000 tensor like this one. Yeah, and then we apply the ALS algorithm. We run it in 5,000 iteration. We initialize the parameter randomly, and what we see here, the success rate is only 36%. So it means that in order to get the perfect decomposition, we need to run many times. Let's go to another second example. It's much harder. We test with the tensor of the size 7 by 7, and the range is still small, only 3 by 3 by 3. But then if you see here, if you unfold a core tensor, in this case, the core tensor will give you a matrix of the size 7 by 9. 7 by 9. And we do something similar. We run ALS in 5,000 iterations. We initialize the parameter randomly. And what we see here, the success rate is much harder, it's much lower. It's only 3%. Only 3%. So it means that it's impossible to get a perfect reconstruction, decomposition for this kind of very small, relatively small tensor with also small range. So how can we do with this problem? We will show you later. So why ALS and many other algorithms for Tensor Train, for this kind of loop tensor network, it failed. The first observation that we see here that if you compute the norm, the Frobenius norm of the core tensor, you can multiply them together, and we have the plot for the norm of the core tensors. We have see here. So when we run the algorithm, for example, 10,000 iterations, the relative error slowly decrease, but the norm of the core tensor increase significantly, very quick.
Hi, Anh-Huy, just a minute. I think there's a question by Landsberg. I'm gonna unmute him.
Yeah.
Hi. So these randomly generated tensors, do you know that even in theory that they could be approximated by a tensor network? Because the tensor network only fills out a small corner of your space.
Yeah.
So do you have an assurance that, say you had perfect numerics, that you could arrive at the tensor via tensor network?
Okay, so so for the first two example, we just try that we saw that the ALS and many other algorithms, it cannot give you a perfect reconstruction. If you try, for example, for this case, you try 10 times. I mean, maybe 10 times, and then maybe in 3 times you can get the reconstruction, the perfect decomposition. But then we try for another tensor. In this case, for example here, it's almost impossible to get because the success rate you see here that it's very small. So we don't. We'll show you later that how can we deal with this problem.
But I don't think that addressed my question. The point, your synthetic tensor, is it at least in principle constructible via a tensor network with these dimensions?
With the dimension 7 by 7, yeah. So we have 3 core tensor. We generated following the expression of the tensor network. This one. So we generated like this in this expression.
Oh, I see. So your tensors are coming from a tensor network.
Yes.
And then you're trying to recover them via numerical techniques.
Yes.
Sorry. Thanks a lot. I missed that.
So the tensor that we decompose here, it have exact decomposition in tensor chains. But the question here that if ALS and any other algorithm, it can give you a perfect reconstruction or not. So we don't generate the random tensor Y, but we generate synthesized tensor from a random core tensor G1, G2, G3. So can I move forward? Hello?
I think it's fine to keep going.
Yes, please go ahead.
Yeah, thank you. So we show you here that even for very small tensor, that's ALS algorithm, and we try many algorithms, but not only ALS, and all algorithms have the same encounter the same similar problem. So it's very hard. This kind of decomposition, it's really hard. So look at this one. So we will show you later the sensitivity, how we define the sensitivity. So if you see here that if we could compare, we show the scatter plot between the relative error and sensitivity. If your model, it has sensitivity very high, so in this case, the algorithm will get stuck in local minima, and it prevents you to get the true solution of the model. So this plot we show here for 10,000 independent run, we generate 100 tensor. For each tensor, we decompose 100 times from different initial point. So before going to introduce the algorithm, so we just show you some relation between tensor train, the loop tensor network, and the ordinary Tucker decomposition, the canonical polyadic tensor decomposition. So look at this, for example, the other 3 tensor network. The loop tensor network, we saw here, we use some, we call it metric multiplication tensor. For example, if we multiply the 2 matrices E and F, we vectorize this. So in this case, we can always compute it from the product of the tensor M. These are the 3 tensor. Multiply with the vectorization of the E and vectorization of the F. Yep. So now we have here the relation. So if we have here the relation, the element Y expression for one element in the Y tensor, you have we already saw that it computed from the trace of vertical slice of A and B and C. So we apply the trick that we showed you before for the B and C and for the A and B, and you have here the trait here can be inner product between the vectorization of C and this one. And finally, we come here that one element in the Y tensor. It can be computed from the projection of the M tensor with vectorization of the on vertical slide on three core tensor A, B, and C. So finally, you see here that a tensor train. This is the tensor trains, and if you flatten the core tensor A, B, and C into a matrix, into three matrices, and you can write here that's the Tucker decomposition. This is a Tucker decomposition. So you see here some link between tensor chain and Tucker decomposition, but it has some special structure. It means that the core tensor is fixed, and we know the core tensor. So these relations we give you the ability to apply any algorithm for Tucker decomposition to find a tensor chain decomposition. And then if you remember that, the M tensor, the multiplication tensor, is a binary tensor. It has only 1 and 0, and it can be decomposed. And in this, many algorithms already find, for example, if we know that multiply of the two matrices, 2 and 2 and 2 and 2, we have the expression algorithm. It have a compute using 7 scalar multiplication. And this is exactly the same that we have here, the M tensor. In this case, they have the size 4 by 4 and have range 7. And the M tensor here can be decomposed to have here binary factor matrices. It have range 7. In this case, we have here, for example, for the K 3 by 3 by 3, you have another maybe range 22 or maybe range 23, but we don't show on the slide. So let's go back. So we have the M tensor. We can decompose M tensor by using in the form of canonical polyadic tensor decomposition, and then we can replace the Tucker decomposition by the structure of the M. In this case, we have here. Look at this. We have here. We have the tensor train in this one. We have this relation to the Tucker model, and we have M can be decomposed by the canonical polyadic tensor decomposition. So now we replace the M, and we have here the parallel tensor decomposition. So we see there's several links from the tensor network. We can go back to some ordinary tensor decomposition that we already know, like Tucker decomposition, parallel decomposition. So in this case, you can apply any algorithm that we know before for parallel to find tensor chains. So let's move a little bit to closer to the topic of the paper, of the presentation, sensitivity of the tensor chains. So in the first talk, we already see some definition of the sensitivity, and we see here some similarity. So what we have here that we want to measure the sensitivity of the model. That, for example, we have the model Y here that follow tensor chain model. It composed from 3 core tensor A, B, and C, and we define some 3 core tensor here: delta A, delta B, delta C is generated draw from the Gaussian distribution with 0 mean and standard variant, standard deviation, sigma here. So we define the sensitivity in this form. And now we already showed you that the tensor chain indeed can be represented by the structural tensor network. And in our paper recently published in Journal of Isolated Topics, so we saw that we can find the sensitivity for the structural Tucker decomposition. In this case, we can find how to find the expression how to compute this sensitivity more efficiently. So let's go a little bit further from the definition of the sensitivity for the tensor chain. We can expand this area. So you have 7 terms, and we only consider the first 3 terms because it depends only on the delta A, delta B, and delta C, and the rest we can skip. And in this case, you see here that this is the interpretation, and because it's independent, so we have here only 3 terms. So now if we compute the first interpretation here, we can have the compound expression to compute the sensitivity. So we skip this, but we show you here the final expression to compute the sensitivity in this form. So how you can compute this? So the sensitivity for the tensor chains, it composed from 3 cotensor A, B, and C. It can be computed from 3 Frobenius norm of each tensor train. This is the tensor train. The first tensor train, you completely delete the cotensor A, and you have B and C. And then for the CA, you completely delete the B, you have the C and A. And then for the last term, you delete the last cotensor, you have A and B. So we have Frobenius norm of 3 tensor train model. And we have here the sensitivity for the tensor chains. So now, okay, we have the model, we can compute the sensitivity, but because the tensor chain is not unique, we can always find some equivalent model to have minimum sensitivity. So, okay, the simplest way that we can scale our cotensor, and we can create a new tensor. This is some new tensor to have equivalent approximation error when we compute the error between the estimated data and the original data, but it has smaller sensitivity. So in this case, we have here the scaling, the factor here can be computed quite straightforwardly. We skip this slide because it maybe go into too much detail. Then the main slide, we show you how we can deal with the instability in tensor chain. So similar to the canonical periodic tensor decomposition, we have degeneracy, and impossible to avoid the degeneracy in CB decomposition. So for tensor chain, it's also similar. This almost impossible to avoid the instability in tensor chains. That then how we can deal with this? So the idea is that instead of generate a new random initial point, because it is almost impossible, because we already showed you that the success rate is really small, less than 3%. So the idea is that instead of start the decomposition from some random point, that we can correct the estimated tensor that we found, for example, using the ALS algorithm, or by using any algorithm for the structure tucker decomposition, or using the algorithm for the Praline decomposition. So the idea is that we minimize the sensitivity. We keep the approximation error still the same as the current approximation error, and this one is the approximation error, the current approximation error from by using the ALS algorithm. We've seen the new tensor would have exactly the same approximation error, but it had the minimal sensitivity. By solving this optimization problem, we can have the stable decomposition. So how we can deal with this problem? Then again, similar to when we derive the algorithm for many other tensor decomposition, we write the optimization problem for each core tensor. We formulate a simple optimization problem, and we update single core tensor one by one. We can use the alternating update scheme. So the idea is that first we write the sensitivity function, the objective function. We fix the B and C. We can skip this one. We have only the core tensor A in this form, and the Q here is the matrix compute from the B and C in this one. So now what we have here, the sensitivity become the trace between A and S. So in this case, S is the A, and we have the approximation. We keep the constraint that the approximation error must be, at least it must be the same as the current approximation error that we have. So we keep this constraint, and you see here this problem is almost convex, so we can find the optimal solution to update the A tensor. But indeed, we can find closed form of that for this problem. this problem can be solved by using the spherical constraint corrected programming. I skip this. So what we do, so we have here the sensitivity correction algorithm. So from one solution by using, for example, by you run the ALS, you have one tensor, and you want to correct the tensor with very high sensitivity. You run this update run from the first call tensor to the last call tensor, and you circulate, you shift the tensor by to the left or to the right by one dimension. And when you combine with ALS, you can run like this one. First, we run ALS, and if we observe the sensitivity is really high, it's the sensitivity the max sensitivity, and we perform the correction. We do the ALS again, and then we check the sensitivity. If it's really high, we correct the tensor again. We correct the estimated result again. So in this case, we will have a decomposition with very small sensitivity. Another approach it does, we control the sensitivity. So instead of using the ALS, and then the sensitivity will go very quickly to very high number. So we decompose the data, find the y-hat in the form of the tensor chains, but we keep the sensitivity to be bounded by some gamma here. And similarly to the duration of the for the sensitivity correction before, so we see here that the optimization problem is very similar. So we just train the objective function to the constraint function, and the constraint function to the objective function. So I skip the algorithm. And again, this optimization problem can be solved and the solution can be found in closed form. So now we go back to the second example that I showed you before. The tensor now it has the size 7 by 7, relatively small, and we apply the sensitivity correction after 3,000 iteration. So at this point we stop the ALS algorithm. We check the sensitivity. We see that the sensitivity is really high. We suppress the sensitivity, and we run the ALS again. And surprise us, from this point, the ALS can, you see here, the approximation error quickly drop to very small approximation error. So we get the almost perfect decomposition. But without the correction, if you run ALS again, you have here almost impossible to find the true decomposition for the tensor chain. So here, I shall use some, again, the success rate. We compare the success rate between three algorithms, the ALS algorithm, the ALS plus with sensitivity correction, another algorithm, we call this a bounded sensitivity. And remember that we showed you before the success rate for 5,000 iteration only 3%, but then if you run the ALS for 10,000 iteration, the success rate now a little bit higher, 10%, but it's still very small. But if you apply the sensitivity correction, you have here the success rate almost 95%, 94%. So almost perfect. So let's move to another application. We decompose the data. In this case, our data is the natural images. We have 6 images.
Anh-Huy, just a quick reminder that you have around a couple of minutes or so left.
Yeah, thank you. Almost finished. Yeah. So we have the images. We have of the size only 128 by 3. We decompose the tensor chain model, and we want to show that without sensitivity correction, we have lower approximation error. We compare here the approximation error between the ALS. We have the relative error, and we have the ALS plus with sensitivity correction. And you look at this one, you see that with correction, with the sensitivity correction, we have lower approximation error with the same number of parameter. And we test it not only for one image, we test it for 6 images, and almost similar result observed for in our benchmark. So we move to another application that is quite hot now. It's how to accelerate the inference time of convolutional neural network. So let's see here the first example here. The convolutional neural network AlexNet. It has very simple architecture. It has five convolutional layers, and it has 3 fully connected layers. So in total, we have here convolutional layer 1, 2, 3, 4, 5, and then we have the last 3 fully connected layers. The main problem in many convolutional neural networks is that it has very high number of parameters. And in this case, if we want to reduce the complexity of this neural network, this convolutional neural network, if we can reduce the size of the core tensor here, we can reduce the complexity, we can reduce the inference time. And how we do this? So this is not, we propose to do this, we already done 8 years ago. So people, they apply tensor decomposition into this one, they apply CBD decomposition to replace core tensor in convolutional neural network. They apply CBD decomposition, but we propose that here that we use tensor trains. But remember that if you apply tensor train using ALS or any algorithm for tensor train, we will face the problem with instability. So what we do here, for example, here we decompose the convolutional layer in the kernel in the layer 2. It has the size 40, 250, and the last dimension is 25. We decompose with this range. We run the decomposition in 13 iterations using the ALS, and you look at this, the algorithm. Okay, you look at this one, you see that the algorithm almost converges. But if we stop the algorithm at this point at 3,000 iterations, we apply the sensitivity correction, and we do the ALS again. In this case, you see here the approximation error now is much better. It's better. So we do same thing for the same layer, but with different range. We see here the same behavior. Thus, we can get much better approximation error than just using the ALS. Look at this. The sensitivity at this point is 21 almost. Let's see here. At this point, you have 3,000 iterations. You have almost 62 million, and this one you have like 200 million. So if you apply the sensitive correction, you have the sensitivity very small, almost 47. So with this, what is the benefit of this one? We saw in one of our paper recently that when we apply the CB decomposition with the very high sensitivity, the network it cannot retrieve the original accuracy because we need to fine-tune the network. So with the benefit here that we have better approximation error, and then we have lower sensitivity. In this case, you see here, we have our model, our algorithm give you almost lower sensitivity than without using the sensitivity correction. If we use ALS, we get the approximation error comparable, but then the sensitivity is really high, relatively high. Yeah, in conclusion, so we go to the last slide. So we showed you that sensitivity in tensor train can be very high, and it prevents the algorithm to get the best approximation even for the data we admit the model. So with sensitivity correction, we can get better approximation, get the model with lower approximation error, but not only approximation error, we have a smaller sensitivity. So I almost finished the presentation, and you can find the slide is uploaded into the website of the workshop.